Hello. So it's a big day today. Calculus, at least at the level we are working at, can be roughly divided into two subfields. Differential calculus, the study of the derivative, which we've been doing, and integral calculus. And today we will start our study of integral calculus, although we will not use the word integral in the following video. So it may seem unintuitive at first blush, but it's often easy to measure a derivative rather than the actual function. Of course, derivatives are themselves functions, but I hope it's clear what I mean. You've got speed cameras, and those speed cameras measure a car's velocity. And if S of t is the position of the car, then the velocity is S prime of t. So we can use a speed camera to measure the derivative very easily. That doesn't give us S of t, it gives us S prime of t. And that sort of raises a very natural question. If you know what a derivative is, can you find the original function? And the answer is going to be a kind of disappointing sometimes, but it's often kind of difficult. But this is the question we are approaching, and it's the question that motivates the following definition. If lowercase f of x is a function, an antiderivative, capital F of x, is a function such that the derivative of capital F of x is lowercase f of x. So, for example, that's that lowercase f of x be 2 times x. Then an antiderivative of lowercase f of x is x squared. The derivative of x squared is 2 times x. So x squared is an antiderivative of 2x. You'll notice I keep saying an antiderivative. Capital F of x equals x squared plus 3 is also an antiderivative of 2x. The derivative of x squared plus 3 is 2x plus 0, which, of course, is 2x. So we have more than one antiderivative. We say that formally as antiderivatives are not unique. But of course, x squared and x squared plus 3 are closely related to one another. And we do have the following theorem. Suppose we've got a function lowercase f of x and f sub capital F sub 1 of x and capital F sub 2 of x are both antiderivatives. Then these functions are the same except for a constant. That is to say that capital F sub 1 of x is capital F sub 2 of x plus a constant. Let's look at an example. An object is tossed upwards with a velocity of 2 meters per second. Now, acceleration under Earth's gravity is negative 9.8 meters per second squared. Let's find the velocity function v of t. I know that this isn't really, it's called applied calculus. This isn't really the kind of application most of you have in mind, but it's a nice example just because it's sort of using everyday functions that are easy to understand. Assuming we know that the velocity, the derivative of the velocity is the acceleration, we can see that we're in this situation where we know a derivative and want the original function. So the derivative of the velocity is negative 9.8. And we want an antiderivative. The velocity is the antiderivative, I should say an antiderivative of the acceleration of negative 9.8. So we want a function whose derivative is negative 9.8. And we think a bit, and we eventually say negative 9.8 times t would do it. The derivative of negative 9.8 times t is negative 9.8. But then we think a little more. We think about this piece of information that I've given you but haven't used yet, that we're tossing this upwards with a velocity of 2 meters per second. In mathematical notation, v of 0 equals 2. And the antiderivative we found, negative 9.8 times t, does not have this property. We want v of 0 to be 2, but in fact, v of 0 equals 0. So does that mean that we've hit a dead end? Does that mean we have to give up and start over again? It does not mean that, because of this theorem. Once we've found n antiderivative, every other antiderivative is just that plus a constant. So once we found n antiderivative, negative 9.8, the antiderivative we actually, negative 9.8 times t, sorry, the derivative we actually, God, cannot speak today. The antiderivative that we actually want is negative 9.8t plus some constant. And to satisfy v of 0 equals 2, that constant has to be 2. So this problem, again, not the kind of application we're really in this class to learn about, but it's sort of very, very typical of how these things work. We have a derivative, we want the original function. We find n antiderivative, but the antiderivative isn't the one we want. It doesn't satisfy an initial condition. In this case, we want this antiderivative to be 2 at 0, and it isn't. We apply this theorem. We say, well, once we found n antiderivative, we found all the antiderivatives. In this case, they're negative 9.8t plus a constant. And then we select a value of a constant so that the thing we want to be satisfied is satisfied. To make v of 0 be 2 in this case, we let the constant be 2. So even though we don't want to mess around with a lot of examples, velocity and Newtonian physics, this is very typical of how this material gets used.